Okay, so the next step in the problem, it tells us that the net force on each block is 0. Calculate the mass m1 in terms of the mass m2. So this is actually really interesting, right? So typically in these problems we've had to deal with solving for acceleration and whatnot. Here it actually tells us that the acceleration is 0 since the net force is 0. Right, so that's pretty convenient. So basically either these blocks are not moving and staying not moving, or they're moving with a constant speed. All right. So we need to find the value of m1 in terms of m2. So I'm solving for m1, and what's really interesting is that the only thing I'm supposed to or allowed to have in my answer is m2. Though I can also have numerical factors, that's fine. But there's not going to be anything else in my answer, right? So this is, again, a very AP kind of style problem. So again, my acceleration is 0. So looking at the mathematical expressions I have, that first one, that ends up being, well, since acceleration is 0, we have 0 is equal to tension minus m1g, right? Which then, that just tells us that the tension is equal to the weight of block 1, which makes sense, right? Because if m1's not accelerating, then those forces have to be equal. Now looking at, now we can't end things here, right? Because we could solve for m1, but the problem is it's in terms of tension and the acceleration due to gravity. We're not allowed to have either of those things in our answer, so we need to replace them with something else. So let's look at then the next equation that we have to find that out. So our next equation tells us that mass 2 times acceleration, so 0, is equal to m2g sine theta minus tension. All right. So looking at this here, we found we can rearrange this for tension. That's going to be m2g sine theta. So then I'm going to combine those two. Since they're both equal to tension, they're going to be equal to each other. So m1 times g is equal to m2g sine theta. So it looks like my acceleration due to gravity cancels out, which is good since it's not allowed to be in our answer. And we have m1 is equal to m2 times sine of theta. We can't leave it at just that. We have to plug in for sine of our angle. So this is the sine of 30 degrees. Since the problem tells us this angle is 30 degrees. Sine of 30 degrees is a very convenient number, 1/2. So m1 is equal, oops, let me write that a little nicer. m1 is equal to 1/2 m2. All right, so there we go. There's my value for m1 in terms of m2. Cool. So that was a pretty neat problem. Things came together very, very beautifully. The last part here tells us, well, now the incline is reduced to 20 degrees and block 2 is released from rest. Predict the time dependence of the displacement of block M2 while the string attached to the block remains taut. All right. So let's see, what do we have going on? We're told a new angle. And so let's kind of scroll up back to my diagram here. We're told, so if this angle is 30 degrees that we have depicted, this remains, let's assume it's at rest, then it'll remain at rest. But if we make the incline a little shallower, well, as you can imagine, just based on your intuition, this means M2 is going to slide up the ramp and M1 will fall. All right, so that's what we expect to happen. So let's see, we predict the time dependence of the displacement of block M2. All right, so this should ring some kinematic bells. All right, we need displacement, so delta x, and we want time dependence based on that. So this basically means we're dealing with the position equation because the position equation is time dependent. So let me write down the position equation and I'll show you what I mean. So our final position is our initial position plus our initial velocity times time plus 1/2 the acceleration times time squared. So since we're dealing with displacement, that's final position minus initial position, which is what happens when we bring x naught over to the other side. So x naught, and something else to note is that we start from rest, right? Release from rest. So the second term is just 0. So we have delta x is equal to 1/2 the acceleration times time squared. So the thing is we now need to solve for acceleration and plug that in to get this expression, to get our final answer. And then that's all we were going to need. So basically we want to have this formula, but so we're allowed to have time in our answer because we want to find the time dependence. Delta x is fine because that's what it says to solve for our displacement. We just need to plug in acceleration. So we need to solve for acceleration to do that first. So now this is going to be a little annoying because going back to my free body diagram step, I did have two expressions here for acceleration. We have m1a is equal to tension minus m1g, and then m2a is m2g sine theta minus tension. We can use those expressions to solve for acceleration because these two equations have two unknowns, being acceleration and tension. So I'm going to use that usual step of solving for tension in one expression and then plugging into the other. All right. So I recommend actually you taking a pause and trying this math yourself, and let's see if we end up with the same answer. Okay, so looking at this here, we've got, actually maybe I'll take a little different approach here. Ooh, yeah, let's take a different approach in solving. So you could solve that system of equations, but maybe let's use that trick I mentioned in one of the first problems we did here, where I solved the system as kind of one object moving. So I'm basically going to do use a trick of any forces acting in the directions of my accelerations, summing them all at once. All right. So what I mean by that is, let's deal with the situation. Excuse me. Sorry. Let's deal with the situation here where I'm going to keep my directions as positive, like stated here in the problem, upward and downward, just because I have it kind of listed that way at once. So when I'm summing my forces, since I'm doing it all in one step, when I'm doing mass times acceleration, it's my total mass, so m1 plus m2 times acceleration. All right, so let me write that over here. So we have m1 plus m2 times acceleration. That's going to be equal to, well, let's look at the forces we have going on. All right. So we've got block M1, negative gravity, positive tension. Then for M2, negative tension and positive x component of gravity. Since, again, we're calling upward and down the ramp positive. So I'm going to write all those expressions down. So again, we have negative the weight of block 1, and then we have the positive tension acting on block 1. Then we have the negative tension acting on block 2, and then we have the positive horizontal, or sorry, I should say x component of gravity, so the component of gravity acting along the ramp, m2g sine theta. We found that earlier in the problem. So since we did this all in one step, we see here that my tensions cancel out, which is what we're hoping. So in the end here, my acceleration is m2g sine theta minus m1g divided by the total mass, m1 plus m2. All right. So we need to simplify this further because we can, and we can actually compute things here because we know that we actually we actually found in the previous step an expression that relates m1 to m2, because we're still dealing with the same system. So even though in the previous step the acceleration was 0, we still found the value for m1 in terms of m2, which we could also write that m2 is 2 times m1, which is what I'll be using. That hasn't changed since you're still dealing with the same blocks. All that changes now, the angle has changed, so now we have the blocks accelerating, but the relative masses have not changed. So my mass 2 is going to be 2m1 times g sine theta minus m1g divided by m1 plus 2m1 gives us 3m1 in their denominator. So m1 cancels out since it's in every term. So that's nice. So my acceleration simplifies to, I'm going to factor out g. So g times 2 sine theta minus 1 divided by 3. So now we're at the point where we can plug in numbers. We can plug in 10 meters per second squared for g, and for my angle we can plug in 20 degrees, and here I would use a calculator because I do not know what sine of 20 degrees is off the top of my head. And when I do this, I get a value of negative 1.05 meters per second squared. My answer here is negative, which makes sense. Why does this make sense? It makes sense because we had originally in the problem we reasoned if we were to change our angle from 30 degrees to 20 degrees, block M2 should slide up the ramp and M1 should fall. When I was summing my forces, I assumed that the opposite was happening, at least in terms of acceleration. I assumed that M1 was accelerating up and M2 was accelerating down the ramp. So that's why my answer has a negative sign. It's saying that when I summed my forces, I picked the wrong direction as positive. And that's fine. That's okay. This means when I'm dealing with my displacement, I'll use the positive value for that because that's the correct expression. So my displacement is going to be equal to 1/2 times this acceleration, 1.05 meters per second squared times t squared. You can take 1.05 and divide it by 2 and have that. That's fine. But I'm going to leave my answer as is. Alright, so here we have an expression for displacement in terms of time to show that it's time dependent. So what's useful about this equation is that we can compute how much each block displaces given the time. So if we say, well, how far did it move in 1 second? We plug in 1 second there, times it multiply by that acceleration, and we get the displacement for that. So it's pretty interesting. But kind of the key to solving this part of the problem is that we had to realize we could use what we found before with the value of masses to solve for it. So overall, I would say this problem is very AP in style in the sense that it led you had you solve the problem in a certain way, and you had to solve it kind of piecewise. So for example, our middle part here, the value that m1 is 1/2 m2 was useful in the next part. If I had you solve a problem like this on the test or something like that, I would be grading for error carried through. So if you found the incorrect expression for mass, but use that to solve for your next part, that's completely fine, as long as you're implementing it correctly. All right. Cool.